you can check, for example, if I put m to 0, right, then this square root is just 1, this becomes 2, this color factor also will take the right value, and it very much looks like that formula there. But m is not 0, and there's some nice aspects to discuss. First of all, let's discuss the issue of the mass in this formula. This is not so intuitive that this is here. It's a spin effect, but never mind. But this one, the square root, has some meaning. You see, if s hat goes to the threshold, to 4m squared, when s hat is really at the minimum level it has to make a top anti-top pair, it cannot be less than 4m squared. You cannot make a top pair then the cross-section is 0. So exactly at threshold, the cross-section is 0. This notion of threshold will come back later in the course when we talk about the summation. So just very close to threshold, the square root goes to 0. So it's a pure phase space effect. It just says that, near threshold there's not much phase space, and the closer to the threshold, the smaller the phase space is. We also see here alpha s squared. That's not surprising. We have a g and a g. You square the amplitude, you have g to the 4th, which is like alpha s squared, with times some pi factors. The final thing to discuss perhaps is this color factor. You have maybe seen CF, maybe some of you have. What it is 1 over nc squared. That's from the average over the two incoming partons, the average over the colors, times the trace over TA and TB. So that is trace over two color matrices, and that is equal to NF-CF, NC times CF. And CF is NC squared minus 1 over 2 NC, so it's 4/3 for QCD. So it comes from the trace over the color group generators. So it has to do with the color quantum number. So the overall cross-section has quite a bit of information. It knows about the threshold of producing particles. It knows about what color state they're in, what color representations they have. It knows about the coupling strength. So there's quite a bit of information in there. And of course, for this particular process, quark anti-quark to top anti-top, it is the only diagram you can make. And that is rare in reactions in QCD, that at any given order is only one diagram. For example, I lost my brush again. Here it is. Let's look at another way of making a top anti-top pair. Of making a TT bar with initial state gluons. We have two colliding beams at the LHC, and the LHC to first approximation is a gluon collider. There's so many gluons at that high energy in the proton. The gluon parton distribution function is very large. The quark ones become relatively small. So we must also look at this way. So let's think of a few diagrams. Here's one. It's a perfect imitation of the quark one, except we now have two incoming gluons. And immediately it's interesting because it produces a non-abelian coupling. Right. Is this the only diagram we can make? So here we have the only propagator here is a gluon propagator. Can we make diagrams with more gluon propagator or a quark propagator? The T-channel one, that's a good one. So that would look like this. Here are the incoming gluons, top, 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 anti-top. Right? It's a T-channel. Any other? Now a bit of a fine point. There's the U-channel, so-called. So this is where you cross them, but to keep these the same. So this is another one. So via GG collisions. This is a bit of a longer formula. I will give it once, and then we can discuss it a little bit. The reason I'm giving it is also because you think, well, that's the nicest ones, so don't bother about something a bit more complicated. Unfortunately, if you make TT bar pairs at the LHC, about 10% roughly of the collisions will have quark-anti-quark initial states. 90% of the collisions will have glue-glue initial states, because there are so many gluons in the proton at that high energy. So if you really want to understand TT bar production at the LHC, we must have this channel. So sigma blue is 4 pi alpha s squared. I'll just give it without discussing it too much. It's a bit of a longer formula. Still fits on two lines. 1 over s hat Cf minus 1 plus 4m squared over s hat beta plus 1 plus 4m squared over s minus 8m to the fourth over s hat squared. It doesn't matter if you don't copy it in great detail. It will not be tested on. Ca minus 1 over third plus 5m squared over s hat beta, almost there, m to the fourth. So not as simple anymore. Log 1 plus beta 1 minus beta. Close. Where beta is the square root. So a bit longer, s hats and 4m squared. Two color structures, a CF and a CA, and the CA comes for large part from this diagram. You see, when beta goes to 0, when you go to threshold, certainly all terms proportional to beta go to 0, this term and this term. But also this, when beta goes to 0, you get this log goes to the log of 1, and you also get 0. So at threshold, the cross-section is 0. You see the color structure factor is a bit different. You see here the average over 8 gluons, n squared minus 1, rather than 1 over nc squared. So there is some structure to be seen. It's a bit longer. So let's see if you can think along. So you have here a cross-section. By the way, the theoretical status of this cross-section of TT bar production. What we have here is a leading order, LO. If you would include one loop corrections to this and also one radiation corrections, combine it all consistently, we'll do that for another reaction in the course, then you would do next to leading order. The status is next to leading order. So it includes two loop corrections to these diagrams, one emission with one loop, and two emissions. All of those ingredients go into the NLO correction. This is a result about 4 years old. It's an enormous calculation, extremely impressive, by Zakon and Mitov, and collaborators and students, Fiedler and Bernreuter. And it's really caused a lot of excitement in the Pheno community, because it's the first time a full QCD process has been computed to that accuracy, a second order perturbation theory, and this is really a huge amount of diagrams, each of which has enormous complications. So, but the upshot is that I may show a plot later in the course when I show some experimental results, is a beautiful agreement with the standard model, also now with a new run at the LHC, which is right on the nose. In fact, the theory error on this is about 3-4%. The data also about the same accuracy, and it just agrees, which is great success for the standard model for QCD. A bit of a shame that there was no deviation. That always would mean something exciting, something new.
How far out was the leading order itself?
It's a good question. So so at the LHC, if I remember right, the correction going from leading to next leading order is about 70%, not small, and the next one is about 10-20% or so. For this process, it is it's a 30% increase, more or less, if I remember right. So the QT bar corrections, smaller size corrections than the glue. In fact, the main culprit of that is the color, because here we have CF. I think this one shouldn't be there. So here we have CF, and also there CF is 4/3, about 1.3. CA is 3. So that's quite a bit. So if you have a 20% correction in one, suddenly you get a 50-60% correction in the other, roughly. So the fact that blue ones come in 8 colors rather than 3 immediately gives larger corrections. That's a bit of an intuitive way of understanding that's a large correction.
Is there any reason that at such high energies, the blue channel Y they dominate?
Yes, it is because well, the fact is, the result of analysis is that at very low energy, quarks are mostly protons are mostly quarks and antiquarks with a bit of gluon. But if you go to much higher and higher energy, you boost a lot of virtual gluons along, and the gluon density, the gluon distribution becomes much larger. It grows also a lot faster because there were so many colors. So at very high energy, the gluon density in the proton is much bigger than the proton density at most momentum fractions. So the reason is that LHC is such a high energy collider. So it's effectively a gluon collider with a bit of quarks mixed in. There's a more intuitive picture that I can tell you, but in practice that's just also what comes out of the analysis. So now maybe also good to make you think a bit about this. Okay, so we have this very precise calculation. We have it agrees wonderfully with the standard model. So then what you do? You say check and go on to something else, or could you do something? What would you do? So let's say, let me give you in. So sigma TT bar theory is about the same as sigma TT bar experiment to very good accuracy.
Look at differential.
That you could do. That you could. This is just a number. You could make it different. And of course, with differential distributions, you need for theory that also exists at next level. But for experiments, you need many more data. You need for each bin and differential distribution, you need lots of data in there, and at the very low bins, you get very few data. So you need more data. But it's coming now. Actually, this is the big thing in top quark physics now: differential distributions. But it's staying at the level of cross sections. What could you do? So we've been calculating this and seeing if it agrees with that. If it works well, you can turn it around. So remember, this still has the Parton model ideas, the PDFs in here, gluon density particularly. So you could use this to fit the gluon PDFs, right, to use the equation in reverse. And this is what's slowly being used now. It's entering these collaborations analyses. So this is frontline stuff, new stuff. So you can really, what you already know in lecture 4, start understanding some of the very recent ideas behind the papers and projects. So you can just turn it around and use this to fit gluon density in a regime where it has never been really tested before or constrained before. And that's what TT bar now does. Since I've given you the theoretical status for TT bar production, I should give you the theoretical status for let me just erase it also. Theoretical status for Drell-Yan. So for Drell-Yan, dy, it is also actually next to leading order. This is a bit easier because there the process is really, as I was explaining, one particle final state in the principle, only an off-shell photon. We ignore the photon decay to the lepton pair, as I was talking about. So this is a 2-to-1 process in principle with next to leading order corrections, and this has actually been known since the late 80s, early 90s, with most calculations done in the Netherlands, not by me, but by Willy van Leeuwen. You met him also. But nowadays we're on the verge of another end, because in the gluon analogous thing to the Higgs production, that is two gluons fusing to make a Higgs, there the status is N-N-N-LO. 3 loop corrections included, and etc. So clearly this is the more sexy process over this, so people have put their efforts to getting this right. Also because the corrections were so large. I mean, your question for this would be the effect of the NLO corrections was 100%, which caused the worry, is this convergence, do we get another 100%, another 100%, do we get 1 plus 1 plus 1 plus 1? That turned out not to be the case. But because this is the reason is because it has gluons in the initial state, more colors, bigger corrections. But then when you have all 3 ends, it's now nicely stabilized, the convergence looks very nicely. And well, more and more Higgs data are coming in, so we have this beautiful comparison with precise QCD here. So that is really the status of particular calculations in QCD, the ones that are really important for QCD. I mean, there are many others, of course, jet production, top plus jet. The one that will be very important soon is TT bar H. This is the production of a top anti-top pair together with the Higgs. Why is that important? Anyone know? Why is that an interesting process? For the Yukawa coupling. So you would get, for example, this. This is making a top anti-top. And then you can radiate off a Higgs here. And the Higgs couples strongly to very massive particles. The more massive, the more stronger the coupling. So here's the Yukawa coupling. So it's actually very tricky because the backgrounds are very, very large and difficult to isolate and to remove. The status here is NLO, and that will not go to NLO anytime soon. The more final state particles, the more vastly difficult it becomes. But we're trying to work out on approximations for higher orders. So the combination of top and Higgs is sort of the next big thing, because who knows the value of the Yukawa coupling in the standard model for the top? It's 0.99, right? It's more or less. So that's worth checking. It's never been checked. So that's the next big thing when you have an update. Okay, I think as a next topic, but that will then be for tomorrow, I'd like to discuss higher order corrections, the technique and the methodology for that, dimensional regularization, how you derive these things, how you should analytically continue it. Some of you have seen some of this before. Renormalization I will discuss too, but I hope for most of you it will still be useful to go over. The goal would be to go to things like the beta function of QCD that shows asymptotic freedom, and to things like anomalous dimensions, which will be necessary for resummation. So all of these things come in when you consider ultraviolet divergences, and which occur in loop diagrams. Would that be okay? Yeah. So there will be notes on that already to be handed out soon, I guess.
After the lecture, we'll just keep the notes.
Okay, very good. So they will be here. The notes, by the way, will start with a chapter on pi naught to gamma gamma decay, which I will not discuss, but I left it in there because it is such a nice calculation. It is a pion decaying via a quark loop to 2 photons, and it does. The loop is ultraviolet finite, so you don't have to do dimensional regularization. But in fact, the technique for doing this is precisely the same as for glue via a top quark loop to a Higgs, and exactly the same function. So if you ever see in the future in a talk or in a paper some weird function arcsine and some logarithm for this particular transition, glue via a top quark loop to a Higgs, the calculation is in that section. You can just go through it. It's a bit subtle. It involves principal value things, so but it shows you also for those of you who have an appetite for integrals, you can feast a bit there. Are there any questions so far on this? Sorry? Cannot happen through here. This happens through a loop only. Just the same as Higgs production cannot happen because gluons are massless. They cannot directly produce a Higgs. If they did, the gluons would be massive. So that's a lesson that it's a leading order is 3 level. Not always. There are leading order processes which start with a loop, such as Higgs production or pion decay. But often this is approximated with an effective coupling, where this dots really stands for a little top quark loop, or for the effect of a top quark loop. But there is no such coupling in the standard model. Yeah. So I think now you've seen QCD from a very formal point of view, Lagrangian. Now we've seen it a little bit in action in 3-level diagrams in Drell-Yan and in top quark production and others. So maybe you get a bit of a sense of both the beauty and the of QCD at the high level, and the difficulties of QCD when you start actually working with it. All things have many things have both such aspects, and we'll see more of it. But even within the diagrammatic techniques, there's a lot to be discovered and structure to be seen, and this is also mostly the theme of the next lectures. Okay, so then we see each other with 2 again for the tutorials. Yeah.